Hello, hello, hello. Hello, there she is. There's the Lila. There's the Mancha. Hello, hello. All right, and hello, hello. And there's the Raymond. All right, all right. There's the Luis. Well, no, no, well, yes, but no. Okay, wait. I'm still in the visuals here. There's the Michael. All right, excellent. Good to see you all. And then there's the Shen with the avatar. Awesome. There's the Tanio with a new avatar, I think. I never pronounce that word correctly. Both my sons make fun of me. Jadith with what I'm counting as an avatar. Of course, Tania with the crazy. I made one in the middle of a faculty meeting, by the way, in the middle of a science department meeting. Suddenly I was showing myself that way, and they were so impressed. So hello, Tania. Okay, now the chat. Hello, hello. Yes. Good afternoon, Luis. Good afternoon, Danielle. Hello, Samaya. Good afternoon, Jerry. Whoa, Shen. Whoa. I'm seeing what's okay. You definitely get. I need to open up some more portals. You guys are Connecticut. Oh my God. No way. Huh. I don't even get. Okay, that's awesome, Shen. All right, sweet. That gets karmic points for the moment and ultimately some kind of point. Oh, you can get points. There's a thing for like images in the chat that counts. Okay, I forget what it's called, the portal, but okay. Nico, hello. Camille, good afternoon. Montserrat, good afternoon. Pleasure to see you, Michael. Thank you. That's very nice. Points for that. Karmic. Raymond, good afternoon. All right, points for that. Awesome. Jadith, good afternoon. Good afternoon, Tania. Okay, we are rock and roll. Oh, did I say Joyce? Hello, Joyce. I see the Joyce. Awesome. Hello, and Harris is coming. Okay. Um, so we're gonna move. I still haven't forgot. On thingy things still exists. Believe me, we will still talk about on thingy things. We'll go back to it. I think we have too much mathematical momentum now to confuse things by turning left. So we're gonna keep doing mathy stuff. In particular, we're gonna transition today from homework one, which we've now officially finished, to homework two, which we're finally up to. Homework two is a lot of sort of practicing and seeing what the end of homework one in action. The summary. Oh, wait, sorry. Oh, you knew that. Wait, is that a joke? Yes, you're probably right. Wait, okay. Oh, no, I think Michael's right, actually. Although he's saying LOL, so I'm not sure if he's joking. But yes, you want logistical announcements like about, or you're just joking because I always do that? Or in term, and also, wait, Shen, can I mute you? Sorry. Hold on.
Wait, sorry, I was referring to the Wednesday announcement that you made for the no class.
You're right. Absolutely. Okay. Yes. Because I'm not even sure if I've said that. Yes. Okay. Thank you. Okay. So you know what? I'm even going to turn the recording off. There's no point. Okay. So the big takeaway from the end of homework one, the big takeaway, well, the big takeaway, the way we wrote it last time was like d2, if d2x over dt squared equals like negative k over m x, then x equals x naught cosine omega t. Like that's the way we wrote it on the lat when we first did it. Now I'm popping it up a slight level. You'll notice now I have like z's on the board here instead of x's, and I have like omega all over the place instead of k over m. Like that's a subtle shift of us moving forward. What do I mean by doing that? I mean, hopefully what I wrote on the board is basically familiar from the end, but now I'm shifting it forward. So what am I doing? So, and if you need me to go back on the board, I will in a second. But I'm saying from now on, let Z stand for, let Z stand for a stylus that actually works. And yes, I ordered two new ones. when I Okay, it's totally illegible on the bottom. I'll read what it says on the bottom in a second. But here's what this board says. It says, let Z, like from now on, when I say Z, as like everything we did in the homework was about X, like position on a physical dimension of space, right? X stood for like displacement from equilibrium position on an X axis, right? That's what X stood for in homework one. Now I'm saying let's go to Z. By Z, I mean freaking any variable, any measurement, like, yeah, anything you can measure, any quantity that varies, that you can measure in a lab, that depends on time, that's changing as a function of the clock. Okay, if Z stands for a generalized measurable dependent variable from now on, then what I'm saying is whatever we just found out at the end of homework one about the mathematics of X along a number line with a physical coil of metal, I'm saying whatever we mathematically figured out about that metal coil, well, it's just true mathematically. So from here on, like the math doesn't care that X stood for position on a number line on a table with a metal coil on it, right? All it cares about is that X was a variable that depended on time. So now I'm saying that all that math is going to hold for the rest of our lives in physics. For the rest of our lives, if ever you can measure something whose value is going back and forth in time, well, going back and forth in time, according to this differential equation, if you can write a differential equation that, well, if you can, excuse me, if you can express the variable in this particular differential equation, this equation that expresses the second derivative of that variable with respect to time, you can write it down that and say that the derivative of the variable with respect to time equals a negative times some constant times the variable itself, if you can have reason to believe that that statement is true, then what that means is whatever that variable is measuring, that quantity is oscillating, is going back and forth. Like in other words, if this differential equation applies, then the Z, whatever the Z is a quantity that's going back and forth, back and forth, back and forth, or if you like, back and forth, back and forth, back and forth on a graph, right? It's going back and forth, in the manner of a cosine graph, mathematically. Like it's going back and forth according to the solution, the cosine solution that we conjectured and verified last week. It's going back and forth cosinusoidally with constants, with an amplitude of Z naught, so to speak, or whatever you want to. Yeah, well, that's called an amplitude with an initial position of Z naught and angular frequency of omega. In other words, like so this is now true mathematically in general. And why in physics do we care about math? Because now what we're saying is if from here on in, if we make any different measurement, it doesn't have to be it doesn't have to be position of a mass on a spring. It it might be position of a pendulum swinging through an arc, or it might be temperature in a cloud going back and forth in time, or it might be the electric field strength of something going back and forth in time. If you measure anything that's going back in time according to Okay. So when I'm saying in English, or trying to say sort of English, I'm saying that from now on, you measure any, and this gets into homework 3, by the way. And if you, it's going to take us a while to go through all these things, but with homework 2, we're going to start practicing the derivatives in the differential equations like I'm talking about right now, and the video practices. And even though at the end of homework 3 it gets into other things like vectors and stuff, which we need eventually, but we don't need right now. If you once you follow the derivative stuff in homework 2, like from this class or from the videos, once you get sort of comfortable with the derivative stuff in homework 2, you'll find homework 3 to be a total fast practice exercise. Like homework 3 is almost like a break. Like if you get homework, it's almost a spot check that you get homework 2. So don't be intimidated. It'll look intimidating at first, maybe, but it's pretty, you could almost do homework 3 based on what I'm like about to say right now. Um, which is this, which is what's on the board right here. It is that, look, I'm saying we studied a mass on a spring in sort of detail because we realized mathematical conclusions about the mass on the spring that then apply to all of these other cases in the natural world in physics. What we're saying from now on is anything, any measurable variable that depends on time in the way that the position of a mass on a spring depends on time, any system that obeys the same math, i.e., the same differential equation as a mass on a spring, turns out to identically behave exactly the same way as a mass on a spring in all physical respects, even if it wouldn't seem that way at first. So, in other words, such as homework 3 gets into, if you were measuring temperature of something, and which doesn't look like a spring at all, right? You're just measuring temperature in gases in a cloud or something, and you notice that the data shows that the temperature obeys, like, so Z stands for temperature, and you notice that the rate of change of temperature of the rate of change of temperature in time, in other words, the second derivative of temperature with respect to time, if you notice that it always seems to be directly proportional to the temperature itself, right? Just like the acceleration on a spring is always directly proportional to the position of the spring. If you notice that the acceleration of the temperature is always directly proportional to the temperature itself, and that the constant of proportionality is a negative times some positive constant, then what you immediately know from here on in, you know that all the math that you already did for a mass on a spring will work for that temperature in the cloud. And the math says that this means that the temperature in the cloud will obey a cosine function, specifically Z naught cosine omega t, where the omega, what I'm trying to say is the omega is necessarily the square root of whatever that constant in the differential equation was, right? So with a mass on a spring, the constant was k over m. So the omega, the angular frequency, was square root of k over m. I'm now generalizing and saying this is a takeaway in general. Not all things are described by a k and an m, but all systems are described by certain parameters, certain constants that are just true of that system, that are just true and known. I'm not gonna write this down. Yeah, that are just true. You write this down. I'm not gonna write this down, but just like there's two kinds of variables, right? Or there's many kind of variables, dependent and sorry. There's more than one kind of variable, dependent and independent, right? Similarly, there's more than one type of constant. Please write this down. Like constant means not changing, right? But something in an experiment or a phenomenon, one type of constant is called a parameter. Like constant number 1 is called a parameter. A parameter is an unchanging material property of the ingredients of the experiment or the ingredients of the phenomenon. A parameter is an unchanging material property of the experiment, such as mass and spring stiffness are parameters. You can know the stiffness of the spring when you take it out of its box and you like measure it, or it says on the box, and whatever the stiffness of the spring is, it doesn't matter how you set it up. It doesn't matter what you do with the spring or where you put it. It's got that constant material descriptive. That's a parameter. Same thing with the mass that you put on the spring. Like you put the thing on a balance, the mass, and it's got 3 kilograms, 0.3 kilograms. That's a parameter. But there's other constants, but constant type number 2 in a system, it might be called a constant of configuration, or even better, a constant condition, often known as an initial condition. So I'd say the best physics term really for constant type number 2 is an initial condition. That's the way you set up your experiment. So for example, in this homework 1, when we set up the mass on the spring, the mass had 0.3 kilograms. That's a constant known as a parameter. The spring had a stiffness of 200 newtons per meter. That's a constant known as a parameter. Where we started the mass off in homework 1, where we like stretched it from the equilibrium position, we held it initially at 15 centimeters. Okay, that is a condition. That's not a parameter. Like we didn't have to do that. We could have done it differently. It might or might not affect the experiment in unknown ways. So, right, but it's still a constant. It was a constant throughout the position wasn't a constant, but the initial position where the thing started, the final place that it would ever go to was a constant. So we call that a condition. Okay. Technically speaking, I'm almost done with this, right? Technically speaking, that initial, and please put this in your notes because I'm just, before I get myself confused, the initial position of that mass turned out to be really important because we found out that even though the mass was, the position was always changing, that initial position became like a maximum displacement, right? Like the farthest out that we held it initially was the farthest out that it ever went. So it became like a turning point. The 15 centimeters and the negative 15 centimeters, they became like boundaries, permanent boundaries for the problem. So the word for that, the word for maximum displacement from equilibrium is called amplitude. I mean, you know that in a way from 7th grade or from 10th grade, you know, from chemistry or whatever. Amplitude, so technically speaking, again, in notes, I'll go back to my board in a moment, but amplitude means maximum displacement from equilibrium, often determined by initial displacement from equilibrium. Amplitude would be an example, another really important example, a related example of a constant of condition, not a parameter. Still with me? Now, why am I saying all this? The reason I'm saying all this is whenever any kind of system, temperature, pendulum on a string, mass on a spring, any system for which the dependent variable can be described by this specific differential equation, anytime the second time derivative of a dependent variable is directly proportional to the dependent variable itself, and as long as the constant of proportionality has like a negative sign in it, then that system will, that dependent variable, the value of that dependent variable will necessarily oscillate back and forth like a cosine on a graph, right? It'll oscillate back and forth, but even more particularly, it'll oscillate back and forth at this solution, this cosine solution. We'll be able to know in advance, not just that it's sort of oscillating, but we'll know specifically that it's oscillating at a certain rate. And the rate will necessarily be the square root of whatever that constant is in the original differential equation. And I'm telling you right now that from the math we did yesterday, that constant in there, it might be a combination of constants. It might be K over M. It might be like you'll see in the lab, or maybe you already did, lowercase g over lowercase l, or it might be, you know, something else for an electric field. But whatever that constant is in the differential equation, it will be a constant of parameters, not a constant of conditions. And so it turns out that we have this bizarre power where we can say, as long as something obeys that differential equation, we know right away it's going to oscillate back and forth at a rate that is determined fully by parameters, not by conditions. In other words, back to a mass on a spring goes back and forth at a certain rate, which we call omega, right? Omega we found last week was the square root of K over M. Why? That's a good memorizer, like that's true as long as it's a mass on a spring, but that's the issue is not to memorize square root of K over M. The issue is to realize if omega the key amazing, and it really is actually, it turns out to be astonishing. The discovery of a mass on a spring is that it doesn't just oscillate back and forth. It oscillates in a way that from here on we're going to call harmonic. Harmonic is a specific type of oscillation. Oscillation just means cyclical motion, back and forth, back and forth. Like your laundry machine can do oscillation. Like I can walk back and forth in the room spastically and call that oscillation. But when I walk back and forth in front of a room, it is oscillation because I'm going back and forth and there's cycles to it, but it's spastic. There's not anything necessarily constant about my cycles. Like maybe, maybe I do one in the first back and forth in a minute and then the next one in 3 minutes or whatever. But if something obeys this differential equation, then the value of the dependent variable, for example, the position of the mass on the spring, it goes back and forth at a rate in time that is constant, i.e. its angular frequency, omega, is constant. Therefore, its standard frequency, F in hertz, is constant. Therefore, its period in time, its time for each cycle is constant. That's already exciting that it's constant. You sort of already were like picturing that or assuming that or knowing that. But what I'm saying is it's so constant. How constant is it? It's so constant that the constancy of it doesn't have anything to do with how you set up the spring. The key point I'm trying to make here before I go on, what is that you notice our spring, it started with a certain stiffness, K, 200, started with a certain mass, 0.3 kilograms, okay. But it also started with this 15 centimeters from equilibrium. Now, at the end of the day, our omega we found was determined by K and M, but there's no X naught or Z naught. There's no 15 centimeters in the equation for angular frequency, the result for angular frequency. So that means it doesn't matter that we started the spring at 15 centimeters from equilibrium. If we concluded an omega and an F and a T that at the end of the day said it takes 2 seconds to make each full cycle, for example, I'm just making up a number. If we found out that each full cycle was 2 seconds, evidently, according to this math, even if we had started the mass all the way out at 45 centimeters, even though each one of those cycles would have been much farther in space, apparently what we're saying is they still would have been the same amount in time. I'm saying, and this is what we call harmonic. When oscillation is like this, it's a very special type of oscillation. Harmonic oscillation is when well, there's all these different ways to put it. They're all the same thing. I'm saying harmonic oscillation is an oscillation for which the angular frequency, and therefore the frequency in the period, because remember, that's just three different ways to describe the same rate. Harmonic oscillation is when the angular frequency is fully driven by parameters, not at all driven by conditions. Therefore, what we're saying is harmonic oscillation is oscillation whose cycling rate in time has nothing to do with how far apart you're asking it to move in space. That's deep. I'm saying the mass, I'm saying the mass on the spring, you pull it all the way out here instead of 15 centimeters, it's got a lot farther to go to get there and to come back. But evidently, it's got so much more potential energy here out at 30 centimeters than it did at 15. It's got so much more potential energy that on average, it's going to have more kinetic energy. So on average, it's going to go a lot faster on the way in. And apparently, the increase in fastness for the longer trips perfectly compensates for the longer trip. I wouldn't have seen that. Is not obvious. It's apparently true from the math. But I'm not saying you should have seen that coming. I didn't see that coming. Galileo didn't see that coming. But it's true that no matter. So I'm saying one last time, and I'm going to move on to homework 2. I'm saying we're now in the realm of discussing or of studying harmonic oscillation. Harmonic oscillation is oscillation governed by this specific differential equation. This differential equation has a cosine solution. The angular frequency of the cosine solution is necessarily the square root, is always, like the solution says. If you've got that differential equation, if the second derivative is a negative time times a constant times the original dependent variable, then the cosine solution oscillates. The cosine like wiggles at a rate that is necessarily the square root of whatever that constant was. It's like that simple from now on. It's just whatever the constant is, or combination of constants is, take the square root of that. That's your angular frequency. And to realize that is to realize that that means you're going to, whether you're studying a mass on a spring or a pendulum on a string or a temperature in a cloud or an electric field strength, you're necessarily saying the wiggle rate, the cycling rate, has nothing to do with how you set up the cycles, nothing to do with how big they are in space. Totally driven, the time rate of cycling is totally driven by parameters, not by conditions. So what we're really saying at the end of the day, and I will now move to homework 2, we're really saying at the end of the day is that we're studying harmonic oscillation now, specifically oscillation that is specifically harmonic. We're going to call it SHO, simple harmonic oscillation. Like harmonic oscillation can get varied, but we're talking about like the simplest cases of it first or now. And in sum, what is a simple harmonic oscillator? What I'm really saying, if you're really following this, is a simple harmonic oscillator is a clock. A clock is something that keeps a tick-tock rate, keeps a time rate, a metronome, regardless of what's happening in space. It's a simple harmonic oscillator is something that separates time from space, if you think, and allows us to rely on a time beat no matter what's happening in the space of it. All clocks, original mechanical clocks, like grandfather pendulum clocks, or watches based on little springs, or even electronic clocks based on electronic, like RC circuits. All of anything that is a clock is at base a simple harmonic oscillator, physically and mathematically, which is to say, anything that obeys this differential equation that we're now going to, this differential equation, which we're now going to obsess over throughout homework 2. The reason we obsess over this differential equation is it describes anything in nature that acts like a clock or helps us keep time or reveal time or anything like that. And I promise you and of course, differential equations are new, so that's we're going to obsess over it. I promise you, this is not only macroscopically the case, but atomically, subatomically, microscopically, the harmonic oscillator differential equation is so important on a microscopic level and on a quantum level that you'll upset. PChem is all about this type of equation. So the more you could follow if you take PChem, which you have to, like PChem is PChem is like intro to quantum mechanics, whether you think of it that way or not. And quantum mechanics is fundamentally hinges around a differential equation built from this. Not exactly this, but built on this. So this is really crucial to nature on the small and the big level. All right, having said all that, we'll try to get concrete and just practice it in homework 2. So let me just pull it up. I'll change the view on the screen. Blah, 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 blah. Now homework 2, okay. Bear with me for a second. Why does it always do this? Okay, I see now. Okay, I'm gonna change it. And I'll like as usual, we have 27 minutes. All right. I'm gonna try at first, I'm gonna do the 5-step method, like as though I would want you to, and then I'll start getting quicker as we go. Hold on, I'm just changing the view on the screen. Okay. All right. So what's happening right now, right from the start, you'll notice that hopefully you recognize this cosine. You see how this is like not unrelated to it. But notice right from the get-go, what we're doing here is sort of going backwards from what we did at the end of homework 1. Like at the end of homework 1, we had a differential equation, and then we like conjectured this solution to it, and then we verified that the solution works. Now we're sort of going backwards. We're starting with cosine functions, and we're asking ourselves, do they solve a certain differential equation? This would be the more natural way to think. It's just this is not this. So this is like the mathematical forward way to think, but it's not how physics works because nature doesn't present us with cosine functions. It turns out nature presents us with laws, physical laws that we translate into differential equations, and then we have to solve from there. So here we're looking at it. So we're practicing seeing what we mean when something does or does not solve a differential equation. So we're starting with the cosine function. And just a quick note, I will from here on in sort of use, like when I use the letter A, I'm using it to stress or emphasize this idea of amplitude as in maximum displacement from equilibrium. When I say X naught, I'm trying to stress like initial value from equilibrium. Generally, they turn out to be the same idea. So I'm basically using them interchangeably. It's just a question of what I want to emphasize. So they mean two different things, but generally, whatever is the initial displacement of something will, if it's a harmonic oscillator, turn out to be its maximum displacement. So please stay facile and flexible with that. A and X naught basically mean the same thing. Either way, they are a condition, not a parameter. So we started with that. So we're going to do the step method here. I'm going to go to the next page. So this is the problem, right? So step 1. Diagram and fact pattern. Now you notice the sheet did not give you a diagram and it looks like raw math. Yeah, fine. All the more reason we needed some kind of diagram. I think I had given you a hint. I think I'd mentioned this. What kind of diagram could we possibly do for something so raw and mathy? Well, it's a cosine function. Let's make a graph. And a graph in physics means a sketch of a graph, just the crucial information, nothing that the vital information. What's the vital information? The axes must be labeled. Otherwise, I have no idea what this graph means. So, time is in seconds on that axis. Sorry. Actually, we don't even know what the units are. I mean, it's a math graph, not all right. So time is on that axis. I mean, time is in seconds, but so time is on that axis. and X is on that axis. I know because of the way, X is the dependent variable, T is the independent variable. And I can tell that the graph looks something like this. I mean, it's a cosine, so it doesn't start at the origin. Right. So that's my sketch of my shape. So a graph has three key things. It has the axes labeled, you have to label the axes. It has the shape, right? And it's going on forever. But then the other point, remember, there's a physics problem. This is like a step method. So the purpose of this whole picture is to have every variable or constant, every letter that's going to be occurring in the math has to appear as a label here. Like this is how I'm defining all the terms I'm using or I'm going to use in the math. So there's still like an A and omega that somehow have to be in this picture. Where are they in this picture? Well, this is A. And right? I hope that, and write me in the chat if that's not clear. But like, how do I know that? I know, and for that matter, like this is negative A, and I know. Right? Like, even if you missed the whole physical discussion of what I mean by amplitude, literally, whatever A is the value that X has when T is 0, because the cosine of 0 is 1, right? So A necessarily, by A, from now on, we mean that point on the graph. Similarly, what's omega? Even if you don't understand all the physics, just mathematically, just from that equation, what omega is, I'm trying to do it in a different color. What omega is this. And this is what I would want you, if this were on an exam or homework, whatever, this is the diagram. Like everything is labeled here in the diagram. And give me. Now, I'm not saying we're necessarily going to have to use capital T in the solution of this, but I'm saying, what does omega have to do with this picture? It has to do with the fact that in this picture, capital T, that we learned last week, capital T, the period, the amount of time for one cycle would be the interval between any two, like points, like any two crests or any two troughs on this curve. That's what. 1 second. Okay. So period can be clearly seen on this graph and as right as an interval between two graphs, or here that would be okay. The diagram's getting yucky, but like that would be period too. And notice period, like we said last week. If you know period, you automatically know standard frequency and angular frequency. Or if you know angular frequency, you automatically know period or standard. They're all three different ways of looking at the same thing, but they have advantages and disadvantages. The period is what you can visualize immediately. In an experiment, you can measure it. On a graph, you can see it. Period is the time interval for a cycle. What omega is the reciprocal of that, but multiplied by 2 pi, like we were saying last week, right? It's harder to see, but that's what it is in this graph. That omega is the number of cycles we're making per time, but measured in radians, not measured in like, because literally the number of cycles in just cycles per time would be literally the reciprocal of period. But on a cosine graph, where the independent variable is measured in radians, um, the the conversion factor, if you like, is 2 pi. There's 2 pi radians per each cycle. So omega is 2 pi over whatever you visually see as the interval between those 2 points. That's my diagram. I'm just looking if there's any questions in chat. I'm going back and forth between the screens. Okay, chat looks good. Okay, so that's my diagram, and that is what I would want. Something like that is what I would want you to do for me. So then step two. Okay, what is the question? So the question is, what is the first derivative of x with respect to t? Now we did this already, like maybe a couple times last week, and in principle, you totally know how to do this from calculus. I'll slow this down slightly. Well, so I'll show you what I would do for this. I would say, so we have to take the derivative of a cosine omega t, right? Assuming that t is it says dx dt. That means t is the independent variable, x is the dependent variable. It means any other letter is a constant, i.e., we treat it like just like a number, just a number that we just aren't specifying. So the way I would do this, especially if this were an exam, especially the first time if we're on exam, so I can make it clear for all the rest. Step 3, GDP. I would say, first of all, in general, so this is my like step 3. In general, if y equals cosine of x, then dy dx equals negative sine of x, right? Like notice I just switched to y and x. The problem is about x and t. It's about physics. But I'm saying, look, what I know in general, or I could say dz dy if you like the z thing. But I'm saying I'm switching to my math brain now and saying, like, what I know from math is if I in general have a function that's some kind of cosine where y is a cosine of x, then I know from math that the derivative of that is negative sine of x. Now, by the way, that, maybe some of us, maybe some of you are more comfortable with that. Some of you don't get that at all and should talk with me about like why that is or why that makes sense, because I think I could show you that it actually does make sense. It's not just a raw memorizer. Some of you have memorized it, so you think you're comfortable with it, but you never cared why it makes sense or not. I'd like to encourage you to shift that view. But whatever it is, so talk to me in private if you want. But that is the case, right? That the derivative of cosine x is negative sine x. So I'm writing it down as a GDP, but I'm also, so it's like A of my G, but also in general, if y equals so I'm still in GDP land here, I'm still in math land here. If y equals f of x, some function of x, and z equals some function of y, right? You remember this from math? If you have a nested function or a composite function, if you have a function of a function, then I'm just going to write it again. So if y equals a function of x and z equals a function of y, so it's a function of a function, then, and I think, wait, does someone need to be on mute? If you're not on mute, maybe unless you want to ask me, please, like you don't have to be on mute unless there's like sound in the background. Okay, whatever. Then if you want to know the full derivative, like if you want to know dz with respect to dx, right? You want to wait, something's happening. Sorry, can I just hold on? I'm going to change the view somewhere. Or is it my thing? Oh, is that noise coming from me? Oh no, it's okay. Okay. Um, then D's, no, notice this. This is starting, right? It just like it may look like intimidating notation, but I'm just going step by step. Like if Z depends on Y, but Y depends on X, then the rate of change, the rate at which Z changes with respect to X, the whole full derivative is the outer derivative multiplied by the inner derivative. You know this, right? You might not have ever thought of it this way, but you know that what I'm talking about is chain rule, right? You just might not have written it this way, and you might have just memorized it as like a thing. But I'm saying it's a thing that makes sense if you look at it this way, and if you think about derivatives. I'm saying, oh yeah, like if you want the outer with respect to the inner, Well, it's the outer to the middle times the middle to the inner because like the middles cancel out. I mean, that's like a simple, that's not like a proof, but it certainly makes it more vivid and apparent in my mind. So, so what does this mean? So this is my step 3 GDP. What I'm saying is at least the first time you do this problem on the homework and on exam, at least the first time you're taking a derivative, you set this up. Like you show me what concepts of derivatives, and yes, they're math concepts, but they're ones that you are, you have in your background. So you set up the math concepts and then you're going to apply them. Now, as we proceed through the rest of the homework or as you proceed through an exam, you don't have to do all this every time. You could say C above or whatever, but at least once it has to be established. So now I'm going to go to step 4. Particular application and work. So I'm going now to the particulars of this problem. Okay. And so I often signal that by saying here in this case, like the function we're talking about is a cosine omega t. So in effect, so this is like really we have like x is a function of y, if you like, and y is a function of t, right? We have like a derivative of a derivative. And in particular, like y is omega t and x is a cosine of y, right? Again, you might be able to do this all in your head. I'm psyched if you can, but I don't want you to right now. I might be writing, I'm hopefully writing out the things that had to occur in your head if you know how to do this stuff, even if they occurred in your head so fast you didn't see them. You're trying to slow down your mental movie and show what you did for future purposes. We're trying to build the life raft on land so that we have it ready to go once we're in the ocean, right? So x is the inner function here, a cosine of y. Sorry, like y is the inner function, it's omega t. Then we're taking the cosine of that. So thus, like here in this case, thus I'm saying the derivative of y with respect to t, like if I just look at the derivative of the inner piece, the omega t, the derivative of that, the derivative of the inner piece of omega t is just omega. You should stop me if you don't follow that. But like that inner piece, it's like saying y equals mx plus b, where b is 0. It's like saying y equals mx. What's dy dx? Well, it's m, right? I can't. I mean, that inner function is just a linear function. It's just a graph that goes like this, and the slope is omega. So the derivative of the inner function is just omega. Omega is a constant number. And so x dy is negative a sine of y, because we already said that the derivative of any cosine is negative sine, right? So if right? So the derivative of the outside is negative a sine of whatever's on the inside. But then according to chain rule above, to get the whole thing that we're looking for, dx dt equals dx dy times the inner. So basically, I'm just saying the derivative of the outer times the derivative of the inner. So it is negative a sine of omega t times all of it times omega, right? It's like this whole thing times omega. So the way physicists, so that could be your answer, but the way physicists tend to write these things is we tend to like to collect all the constants at the beginning if we can and focus everything on the variable. So we would write it. So we would write our final answer like this: negative a omega times cosine of omega t. that is our final answer for number one. Again, I will try to not drag out all the other ones quick, but that's like what you do. So that's step 5. Final answer circled. So the first derivative is negative A omega cosine omega t. That's what it asked me to do. So I did it. Like whether it seems to mean anything or not, I did it. Right now I'm going to move. Now I'm going to start. Now, if that's clear, I'm looking at the chat. If that's clear, oh, that's a good question. I mean, Michael's question, will homework 3 still be doing Wednesday? All right, no, I'll postpone it right now. Good question. You can all give Michael points for that. I'll postpone it right now to Monday. I mean, the truth is you could do it. You actually could do it now, but yeah, fine. I'll postpone it right now before I forget. Hold on. See how this works? See, participation's really good, isn't it? Hold on. I mean, I can't always do this, but no, it's a fair question this time. Hold on. Let me just do it even especially, I'm going to just take Michael's question to mean, oh, I understand what you're saying so well, Yaviram. It's so deep how deeply you're helping us with problem 1 of homework 2. But since you're only getting to homework 1, it'd be nice if we had more time on homework 3. But yes, it was so deep, Yaviram. You're so awesome that yeah, no, right. So yeah, hold on. I'm changing it right now. Changing it right now. Great. Thank you, Michael. That just helped everybody. Also, just give me one more second because I have 6 minutes. And that also means I don't have to like rush the next thing. I'm doing it for the other class too. Michael just benefited the other class also. I mean, sorry. So give me a second before. Okay. Thank you, Michael. Okay. So, oh, and someone's here. Okay. Oh, sorry. That was a direct. I'm so sorry. That was a direct. That's totally my bad. I'm sorry. Um, well, thank you anyway. Sorry. I totally did not realize that. Okay. I'm just going to move on. I apologize. But yes, but it was good. It was good. I'm sorry. I have to be more careful about that. So I'm going to at least finish this problem. Oh, wait. Oh, there's something else in direct chat. Sorry. Yeah. Wait, what did I say? Wait, did I write? Wait, no. Oh, sorry. Thank you. Oh, another direct chat person. Thank you. And you should definitely submit. Both of you are totally helping the class. I'm sorry. I'm sorry. You're absolutely right. And okay. And you should submit for points for that correction. Yes, I carelessly wrote down. Yes, this is supposed to be a sign here. Sorry. Yes, thank you both. Yes, thank you, direct chat person. The first derivative is sine, and then I just carelessly wrote cosine. So that's our first derivative. That's the answer to the question being asked in the homework, and it just is the answer. Right, you're right. And please just raise your hand quickly if you caught that correction. Did you catch that I just corrected that I made a mistake and corrected the typo of cosine to sine? Just raise your hand if you got that. Okay, cool. Good enough for, well, just 3 people. All right. Well, okay, good. Plus it'll be in the PDF and okay. Therefore, great. Thank you all. So with 3 minutes left, I'll just finish this problem. Then it goes, and I won't do the step method or anything. Then it goes like part, Sorry. It goes, then it says, what's the second derivative? Well, and you could say C above, by all the same reasoning, well, the one thing I'm going to say now is what I know is that the second derivative of x with respect to to t necessarily equals the derivative with respect to t of the derivative with respect to t. Notice, I'm just pointing this out. This is a GDP.
You know the work study places we got last year, the green ones?
Yeah.
What size do you want this year?
Oh, what I want?
What size?
Large.
Stop, please. Wait, this keeps happening, Shen.
Yeah,
What's
another
going
freeze.
on?
Yeah, come on.
Wait,
It's
Shen.
like a work study
What's the
thing.
colored stuff?
Maroon?
Mm,
Wait, Shen, can you please mute?
Are you working?
maroon.
Why does this keep happening? Okay. There's not a portal for that. Okay. Notice this. You might think it's obvious. Oh, the second derivative is the derivative of the derivative, but just notice the way I just wrote that. Doesn't that sort of show you why the notation is all funky like that? The reason second derivative, if you've ever been confused by derivative, like that we put the 2 in the middle on the top, but then the 2 to the right on the bottom, that used to bother me so much that when I eventually just accepted it, it became another one of those things in my brain where it's like, oh, math doesn't make any sense. They just do weird crap and I just have to accept it. No, math does actually make sense. There's actually a reason behind all this notation. And the notation often really helps you understand how to do things if you take it seriously. The reason second derivatives are written that way is because it's not a multiplication of two derivatives. It's a derivative of a derivative, just so you can know. Okay, yes, yes, yes. You'll still get a lot of yes. You will still, yes, you'll get credit even if you don't do every one of these details, but this is the ideal to follow. I'm looking at direct chat. So, and you don't have to write it every time, but at least once. But just notice the second derivative of something is the derivative of the derivative. That's why it's written that way. So here I would say here, therefore, and this is where we'll end, the second derivative equals, well, oh, and like if y equals sine of x, then dy dx equals cosine of x. Notice now that there's no negative sign here. Derivative of cosine is negative sine. Derivative of sine is positive cosine. Like I can show you that in private y, but it's the case. So here, when we take the derivative of the thing we already had, the negative a stays. The cosine, the sine turns to a cosine, but omega comes out again from chain rule. So now we get this, right? Like this is the key takeaway for it. When we take the second derivative, the negative sign stays with us. It's now 420, but the omega gets squared. The key to that is when it goes on to B. I'm just going to say vocally. So B, when it says, is a cosine omega t a solution to blah, 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 blah? The answer is yes. And that's the key point to this whole thing. We are showing that the cosine solution does solve the differential equation because we could switch the a and the omega around. We have negative omega squared times a cosine t. I'm going to do it right now. I know this is, if you have to go, go. If not, I'm finishing right now and I'll just hang for questions. But I'm saying we got omega squared a cosine omega t and a times cosine omega t. That was x in the first place. So we did just find out that not the first derivative, but the second derivative of x with respect to t is negative times a constant called omega squared times x. So it is a solution. This thing is a harmonic oscillator. That's what, so we just went forwards what we sort of did backwards last week. Okay, that's it. You've been very, very patient. You can go. I'm going to hang out for a second if there's any questions, you want to make any appointments or anything, but thank you. And thank you for the corrections. Okay. And you've been very patient. All right. I'm stopping the recording.